Hi, thank you very much for being here. Next speaker, we'll talk about concurrency and parallelism from the ground up. She's Amber Brown. She's very well known to PyCon and as a computer owl who works in Python, networking, and data. So she's been a fixture in the past conferences, so you've probably seen her speak already, and that's why you're here. She's the Twisted Release Manager, and she's a general code troublemaker. Please welcome Amber Brown.
Hello, everyone. Can people hear me? Is it on? Add on. Okay. Technical issues.
The light is green.
Okay. Cool. Well, I'll just speak louder. Hello, everyone. Today, I'm here to talk about implementing concurrency and parallelism from the ground up. This means less about what Python module you import and more about how it's actually done at the level of the CPU, the operating system, and then onwards into user space. I believe this is important because it might not be clear how, when you're developing a concurrent application in Python, how it's actually handled underneath you. The techniques to run software concurrently and in parallel have been around since the 60s on computers as old as the PDP-1. But it was much longer until such features came to consumer hardware and consumer operating systems. Both macOS and Windows had similar paths, but I'm going with Windows as the context as I have personal background with it. It is rather fortunate that sequential consumer versions of Windows gradually introduced concurrency features as it got more advanced, so we can use it as a good sort of viewpoint for explaining how and why things are today on modern computers. So I am Amber Brown. I'm probably best known for my work on Twisted and related projects. During the day, I work at Jelly Australia on renewable energy and storage. And you can find me at Twitter at @HawkyOwl or HawkyOwl on GitHub. So it's 1983. There was nothing, just a DOS prompt. I don't expect you to understand all the lingo, as it were, so let's have a quick primer on terms. The most important two terms in this talk are concurrency and parallelism. They are similar to the user, but vastly different in requirements and operation. But to the user, they both achieve running multiple things at the same time. Concurrency is where multiple tasks run interleaved, each task running for a small enough amount of time that all tasks have some work done on them on a human timescale. You never actually run two things at the same time, but it's a good enough illusion. Parallelism is where two tasks actually run at the same time. This necessitates two or more processing units. So let's have a look at how programs run to understand why running them concurrently can be hard. Programs are stored in an executable format, are little more than a sequence of instructions. The central processing unit, or CPU, executes these instructions in sequence. As an example, here's an excerpt of the instructions that make up a part of Python. What's shown here is the disassembled machine code organized into instructions. Something to note is that nearly every instruction relies on the previous one succeeding. You can't run them in a different order, as each instruction relies on the state of the application being what it expects. On a higher level, in programming languages, the underlying machine code is hidden from us, as it's transformed into a program from a program code like this into the machine code that does what the program represents. You can see the usage of two functions here in this QBasic application. There's print, which prints text to the terminal, and end, which finishes execution of the program and returns to the operating system. If we were to compile and run it, we would get this: the print functions in the exact order we programmed them. One will always come before the other, and end will always come at the end. Nothing in between, all in the same order, always. Classical desktop operating systems like MS-DOS only supported one application at once. You type the application name in, hit enter, and the application ran until it finished, allowing nothing else to happen on the machine. This is fine for things like games. When playing King's Quest, you wanted to play the game, but this was a sticking point for general and office computing. In the business world, you want to run many things at once. Checking to see if you have an email shouldn't involve completely shutting down the word processor you are writing a report in. So let's fast forward to 1985. What is the future? The future, of course, is Windows. Windows is named after the thing it brought to the IBM PC world. These windows were little containers that held an application, so you could display multiple on the screen at once, or minimize one, but keep it running while you looked at something else. At this time, we didn't have multiple CPUs in desktop computers, so using parallelism to run all of these applications at once was out. We needed concurrency, which was exactly what Microsoft provided. So how did Microsoft run multiple applications at once in Windows? Windows 1.0 implemented what is called Cooperative Multitasking. Each application had to specifically support Windows, using its APIs to cooperate with the rest of the system. This was built on trust, a trust from the application that would get time to run frequently enough to provide a good user experience, and Windows would trust the application to not monopolize runtime. The API that Windows implemented looked kind of like this. Windows implemented a message queue, in which an application would periodically ask for a message while running using the getMessage function. This system call would transfer control to Windows, which would either provide a message or suspend that application and pass control to another, causing the original application's thread to block until Windows was given control back later and provided it a message. The application could potentially use a different API called peakMessage, which would not block. This allowed an application doing heavy processing to still be notified about events from Windows, such as key presses, without giving up control. This gave absolute control to the application when it should allow absolutely anything else to run on the machine. Not even Windows could wrest control from the application once it was running, unless some form of interrupt called into it. This model meant that you had to explicitly write applications for Windows, which meant a large amount of applications had to be rewritten or modified, not only to support concurrency, but also Windows' graphics libraries. And if the application didn't yield enough control to Windows, other applications could seem laggy, or even things like cursor movement could be affected. The implementation, however, is simple, relatively easy to implement on the operating system and application side, and doesn't have a lot of overhead. One important thing that Windows 1.0 had, that most versions of MS-DOS didn't, is virtual memory. When running concurrent applications, you mainly want two things. The first is that you want applications to be portable. This means that the application doesn't have to rely on any certain memory segments being free, or it being placed in a certain region of memory. If multiple applications accessed fixed points of real memory, it could mean chaos, with one or both applications stopping working. The second is that you don't want any one application to be able to mess with the memory of any other application by default. Keeping applications separate in memory means that no one corrupt application could affect anything else. Virtual memory is generally implemented by a memory management unit. This MMU, when referencing blocks of memory, will refer to a page table to find where the memory actually is in RAM. This means every application on the system could put something at 0x0, but it will actually be put somewhere else, with the application none the wiser. This is also useful for older applications that may expect to control all of the memory. Virtual memory is invisible to the application, so it doubles as a compatibility shim. So, we have multiple applications now. And with virtual memory, they are mostly none the wiser about each other, and all play nicely. However, the software kind of has to behave in how it does concurrency. And software doesn't behave a lot. So say it's 1994. What's the future? Windows 95 is my favorite operating system. I say this without any irony because it really was one of the turning points in my life. It was a very wonderful thing to get to see. Just look at the maze graphics. So cool. Remember that we're in 1984. This is impressive. Anyway, Windows 95's advertising focused on two things. The first was multitasking, and the other was the internet. The internet didn't really do much but cause problems for Windows for the next decade and a half, but the multitasking was all right. Windows 95 implements preemptive multitasking. This is where the operating system takes control from the application, preempting it, rather than the application giving control back to the operating system like in Windows 1.0. The operating system gains back control through the use of interrupts from a real-time clock. Interrupts are a CPU feature that allows a code routine to be ran according to some trigger, and modern CPUs ship with a real-time clock that can provide that trigger after a certain amount of time. When we schedule the runtime of different threads, the operating system needs to decide how long to let it run before switching control to another. This amount of time is called a time slice, or in Windows lingo, a quantum. Changing between threads is expensive, as we'll see, but if you don't switch frequency, the illusion of concurrency becomes obvious to the user, and applications seem unresponsive. So picking the right time slice length is important. On Windows XP, time slices are generally 15 to 60 milliseconds, and on Windows Server they are affixed to 120 milliseconds. The length of this time slice has a bottom limit, which is the tick rate of the operating system kernel. This tick is what is set in the real-time clock, and hands control back to the OS every so often to update things like the system clock, process internal events, and most importantly, reduce the running thread's time slice. Operating systems of the time would have a server and desktop kernel, with different tick sizes for each. Every tick, which is about 15.6 milliseconds on Windows, 4 milliseconds on older desktop versions of Linux, and 10 milliseconds on server versions of Linux. Since Windows' tick is 15.6 milliseconds, that determines the minimum time slice it can allocate to 15.6 milliseconds. Linux had a configurable tick, and therefore configurable minimum time slices. Overall, the operating system has to be careful about what time slice it allocates to applications that the user may be interacting with. Windows will give the active Windows whole process a higher priority, and therefore larger time slices more often, to keep things responsive to the user that's using the application. But giving a too short time slice to the only thread that needs to do a lot of work, and then causing excessive switching to otherwise inactive threads, means that time is wasted and overall throughput goes down, which is bad for servers. So, when a thread is either preempted or cooperatively gives up control, what needs to be altered? Software is generally written as if it is the only thing on the machine and it will run forever. To maintain this lie, the operating system has to save the state of the thread before it preempts it and restore it when it runs again. Ideally, a thread will never know it has been preempted and will still run correctly. To do this, the operating system must save the current working set of the thread to memory. The registers, which can be thought of as high-performance bits of memory on the CPU, represent the current CPU level state, the virtual memory representing the rest of the state in RAM, and the program counter representing what instruction inside the binary that the thread was executing. Many of you probably know of multithreading. It's where, in the same process, you create a new thread to do some task without stopping the current thread. Every process, which responds to an instance of a run binary, has one or more threads. Each thread is a chain of instructions with its own stack, CPU registers, and the like, but shares its virtual memory pool with the other threads in the process. The process, however, holds the state about what user is running it, what binary is running, and the memory it holds as a whole, so there's a difference between threads and processes. Preemptive concurrency creates new problems. Each thread may be preempted at any time. The thread doesn't know that. What problems can this cause? The largest is race conditions in multi-threaded code. Let us imagine this code being run in a thread. It reads a boolean from memory, flips it, and then saves it back, and then reads it again. Simple. If it is the only thing running with no preemption, we can expect this output. But what if, in the same process, we have two instances of this code in two different threads? Thread 1 might get up to the comment, having read a false, written a true, and then been suspended. Thread 2 may then start and run to completion, having read the true, flipped it back to false, and saved it back. Thread 1 then resumes, and what does it read before exiting? It reads false, as thread 2 wrote. This is an example of a race condition. So it's 1995. We've still got one CPU, but we're running multiple programs on it that might not play nicely, but that's okay. Virtual memory and preemptive multitasking means that all works fine unless someone writes some buggy multi-threaded code. Let's skip forward to 2001. Windows XP was one of the first consumer operating systems where we could start taking advantage of parallelism and pinball. Simultaneous multithreading, known as marketed as hyperthreading by Intel, is a way of providing parallelism without having two true cores. It works by duplicating the instruction queues, creating two logical processors that the operating system can address and use. These two logical processors feed into one physical processor, more efficiently filling in gaps where one logical processor may be waiting for data from cache or RAM by processing the instructions of the other, or by combining instructions from both that the physical processor may be able to run in a single instruction. Later in Windows XP's life, multi-core processors became very common on consumer computers. This added a new layer of complexity, as true parallelism was now possible. And one of the major features of parallelism is causing your threaded code to become even more broken. Now, on any line of this code, the memory at 0x0 can be changed. Even if you have the whole time slice and your thread is not preempted, another thread can modify the memory you are looking at. This increases the likelihood of race conditions, as some dangerous code may have always fit in the fraction of a time slice and never presented itself as an issue until now. The proper way to implement this would be to wrap the critical section, the parts that require the data they operate on not be modified, in a lock of some sort. Now, mutexes are a different name for lock, named as a mutual exclusion. Semaphores are a type of mutex and come in two types, binary and counting. Binary semaphores are locked or unlocked, which is useful for protecting resources that can't be mutated or accessed by two things at the same time, such as memory or a socket. Counting semaphores are when multiple things can access it, but only up to a certain number. You may have a thread pool with a certain number of threads, and a counting semaphore controlling when a task may be sent to it. Task must wait until the counting semaphore is not at its limit to try and acquire a lock. One of the major problems with locks is that they can be a source of errors themselves and fall prey to a race condition. Just like the examples of reading Boolean from memory before, a naively written lock can read a false, try and set a true, and not have done it in time for another thread to read a false and set it to true as well, giving two or more threads what is meant to be an exclusive lock. The lock needs to be atomic. That is, the read-write operation happens instantaneously to all other threads. That is, looking before you leap may actually cause problems, as looking and then deciding whether to do something is more than one instruction. However, modern CPUs ship with atomic instructions to assist with creating better locks, one such instruction commonly being called a test and set. When a thread wants a lock, it runs a loop which uses a test and set instruction, which tests for false and atomically sets it to true if the test condition is true, otherwise looping and trying again. This can cause problems too, though, as if you have 10 threads waiting to acquire a single lock, 9 of them will be spinning in a loop, trying to do that test and set, which is only one instruction, so it's atomic. But they'll just be wasting CPU time, as one thread will hold the lock. It's not a fixed queue either. There's no queuing. It just is whatever thread grabs the lock when it's vacant will get it. So one thread could be waiting for a very long time, and one thread that's not been waiting for a very long time could get the lock rather than the one that's been waiting. There are more complex locks that are fairer that build on top of these primitives, though. Code that properly uses locks, doesn't share global state, or otherwise doesn't fall prey to multi-threading issues is called thread safe. Code isn't thread safe by default, so it's important to verify that it is before using it in a concurrent environment. Due to the advent of symmetric multiprocessing on consumer hardware, applications are getting more and more thread safe and are being written to take advantage of the extra cores that we have at our disposal. Let's move forward. So year 2007, the future. Over the next decade, as it becomes increasingly hard to make a CPU faster, we end up with more CPUs on a die. On the server, which may have 2 processor sockets, 32 core configurations, each core with multi-threading, can mean your system sees 64 logical processors. This introduces brand new problems, such as cache coherency and worse cache misses. Many CPUs share some level of cache between physical cores, so on a dual core, being moved from CPU 1 to CPU 2 may not be such a big issue. But if you're on a 64 logical core system, and you get moved to an entirely different die, or otherwise between cores that share no caches, you have now lost all the benefits that those caches provided, as well as leaving potentially outdated caches behind. If you were to switch back to that core later, if that cache wasn't flushed, then your application might just use it, and it might lead to incorrect behavior. Windows 8 killed off the CPU tick, instead scheduling it dynamically. This is good for power saving, as it prevents the CPU being woken up every 15.6 milliseconds to sometimes process maybe nothing but some timers. This has ramifications for time slices because 15.6 milliseconds is no longer the smallest a time slice can be, and it makes larger time slices more efficient, as the operating system is not interrupting them needlessly. On Linux, the introduction of Tickless kernels meant that there was no longer a difference between a server and desktop kernel. This change happened, I think, Ubuntu 12.04, or just after that. So now, desktop and server, there's no difference in the kernel. The CPU is not the only thing that can have concurrent access troubles. Lots of tasks don't fit how modern CPUs execute instructions and perform better on the kind of processors that graphics processing units have. This includes 3D rendering, video encoding and decoding, machine learning, that sort of thing. However, GPUs generally don't have memory management units on them, and some applications could corrupt the graphics or data of other programs. Windows Vista and Up has a display driver model that provides both memory segmentation for GPU using applications, as well as GPU time slicing, disallowing any one application from monopolizing it. So we've talked about CPUs and operating systems a lot. What does this all mean when we apply it to Python? It's really easy to write multi-threaded Python code. The problem is that because of concurrency issues inside the interpreter, Python doesn't actually run Python code in multiple threads. The global interpreter lock, or GIL, means that only one thread in the Python process is actually executing Python at any one time. This has the benefit of making a lot of concurrency problems not happen by making Python effectively non-concurrent. This doesn't shield you from C extensions, however, which release the global interpreter lock. So if you pass a Python object into a C extension, it can potentially read and access it in a non-thread safe way and cause otherwise impossible bugs. The C extension itself may not be thread safe. Another option is to avoid threads as much as possible and instead adopt cooperative multitasking practices. Python asynchronous I/O frameworks such as AsyncIO, Tornado, and Twisted implement this, as do frameworks in other languages like Ruby's Event Machine and Node.js. But since we're only in a single thread, things that block need not be used. This means no blind calls to sockets or files, and we have to somehow support every connection we might make to the external world without putting it, we have to support being able to make external connections without putting it in a thread. The problem of how to handle many connections in one thread is a big one, but not insurmountable. Every modern operating system ships with some method of implementing non-blocking asynchronous I/O. Every Windows program is event-driven at the core, so I/O completion ports has a callback design that fits very well in it. On Linux and Unix-based operating systems, we have select, epoll, and kqueue to pick from, depending on which kernel. Use these kernel APIs by calling them with lists of sockets, and it tells you which ones you can send or receive on, and if you can't send or receive on them, you just buffer. This fits well into an event-driven system. These techniques work and it does scale. It's how a Twisted or AsyncIO application can support thousands of connections on a single core, and how Nginx can drive massive amounts of traffic efficiently. Plus, you can spawn up new processes and communicate with them asynchronously as well, allowing you to execute long-running, high-requirements tasks that don't otherwise fit the event-driven design, but communicating with them in a way that does. Of course, we're still at the mercy of the operating system thread scheduler. Even if we're not paying the costs of thread switching in our application itself, we have to play nice with everyone else. Reducing thread contention is important, as if there's less threads competing for runtime, your time slice can be bigger. If you still do have a lot of threads, but multiple cores, you can use an operating system feature called affinity to force a process to stay on a particular core. If you can keep your important worker thread on its own CPU and set its priority high enough, you're sure to get long uninterrupted time slices and will increase the performance of your single-threaded event-driven application or even your application that uses threads. If you do need to use threads, and let's face it, some particular APIs don't come asynchronously, you can reduce the memory overhead by altering the stack. Every thread needs its own working stack, and sometimes that can be set far too high. If you have 100 threads on your system and each had a megabyte of stack, that's 100 megabytes of overhead right there. You can configure how big the stack size is for your particular application when you spawn the thread. Usually, if you start a thread to do some processing, you'll want some data back. But communication between threads can be difficult if you don't have something like the GIL to protect you, as you have to manage your own synchronization. If you put this task in another process and communicate over some sort of bidirectional bus, such as a Unix socket, pipes, or TCP, then there is no directly shared state involved. This does now make your application effectively a distributed system with all the problems that has, but task managers exist to take some of the issues out of it, and there's ways to get around it. Additionally, if you communicate over some pipe with different portions of your application, it's easy to turn those pipes into, say, TCP, and move it off the machine if it gets too big. We all know where that leads. Microservices. Thank you. We've still got 5 minutes. Okay. We have time. Yeah, I'll take a question or two.
Thank you so much, Amber. There's time for one question or maybe two if they're very short. So please try and make them short and make them questions, as they say. Anyone?
Please do not ask about the GIL.
Also, don't ask about the GIL. No?
No one?
No takers? I do have one.
Okay.
The story about concurrency lately in Python 3 and also backported to Python 2 is async I/O. What is your take on that as a practical solution and the future evolution of it?
Well, so just to note, the Python 2 backport of async I/O is deprecated and you shouldn't use it. So you should just use Python 3, basically. Python 3 is great. Async I/O, well, the method of doing what async I/O has done has been proven to be popular in Python in the past with Tornado and Twisted. The future of async I/O and all of that is basically getting it normalized in the community, that you ship libraries that are asynchronous compatible, because right now if you pip install requests and use requests in your async I/O application, it just doesn't work. You'll end up blocking and then you're just throwing the event-driven system away. So I think the future is people adopting it, seeing the benefits of it. It does have its benefits, it does have its downsides. If you're doing a lot of CPU sort of stuff, then multiprocessing or multithreading, multiprocessing if it's all in Python, is a much better idea than using async I/O. But a lot of us write web applications that maybe have lots and lots of users, and supporting those in a classical system like just running Django with Gunicorn, you end up with a lot more servers and a lot more threads than you maybe want to, while if you're just talking to a database, which is a easily asynchronous operation, then a single async I/O application can serve thousands of users a minute. So basically, the future is all depends on people using it. If people adopt it and pick it up, then it's going to be a very bright future. If no one picks it up and we all just keep doing what we're doing, then it'll suck, and it'll, not advance. So you should probably look into it if you haven't. Or Twisted. Twisted also works if you're stuck on Python 2. Twisted and async I/O have compatibility layers between each other, as do Tornado, so you don't have to be sort of beholden to any one of them. You can sort of pick and choose. We're working on that a bit more. Python 3.7 will have a lot more features in that department, allowing you to sort of pick and choose your asynchronous framework and have them all cooperate together in the same process without having to put Twisted in one thread and async I/O in one thread and working out how to communicate between them. They'll all just run on the async I/O event loop. So that's my mini rant for that.
Thank you very much.